then once we are kind of rolling with this, I'm going to let you guys see if you can remember a little bit about this and see if you can complete this on your own. So let's read this together. It says g of x equals x to the 1/3, f of x equals 1/4 x. On the interval from 0 to 12, what is the maximum vertical distance between g of x and f of x? So I kind of thought we'd mix this up a little bit, and I thought maybe we'd start off by graphing this on our calculators. So if you would, grab your calculator, and will you please graph g of x and f of x? We'll get a look at this graph, and then we'll kind of make a decision on how we would proceed from here and figuring out some candidates and all that good stuff, kind of like what we did last time. Let's start off with a graph.
Window, just the interval.
I'd make my window from 0 to 12. Yep. I don't know about my y's necessarily, but I'd go 0 to 12. That's pretty reasonable. You might have reason to change those sometimes, but probably okay on this one. Am I doing that right, roughly? It's pretty close. They do intersect, don't they?
Mm-hmm.
Yeah. Okay. It's kind of a tough one, isn't it? Let's stop and think for a second. What we're supposed to be finding here? It says, I'll highlight it for you. What is the maximum vertical distance between g of x and f of x? And so if you think about it, all we're really doing is we're taking a vertical line from, here to here. Oops, it's supposed to be vertical. From here to here, here to here. We're basically trying to figure out where would that vertical line be longest. Does that make sense? What is the maximum vertical distance between g of x and f of x? Okay, so it's really hard to tell on your graph, right? I mean, isn't it pretty obvious that it's not right there? I mean, wouldn't that be the shortest distance between the two? And probably right here as well? That's when they're closest, right? Because they're right on top of each other. But as far as trying to find the vertical distance, you might be tempted to just be like, well, I think it's over here, or I think it's in here somewhere. It really is. I was peeking over your shoulders. It's kind of hard to tell on the graph, right? So we're going to have to use a little bit of calculus to help us with this. And so what I thought I'd do is kind of set you guys up for success and see if you can run with this as far as possible. I thought we would set up an equation for that vertical distance. So I'm going to call that d. And in this case, what would you guys say this d? And like d for distance, you're going to find it's a little misleading, but I think we'll use it for now. How could I express the distance, the vertical distance between these two functions? Anna, what do you think?
Difference between g of x and x.
Yeah, so I like it. So g of x minus f of x. Somebody might have said, you know what, I think it should be f of x minus g of x. And if somebody said that, they would not be wrong. Because since the two graphs cross each other, you could really say one or the other is like the high function, depending on where you are. And so I think it's going to work out okay if we just go with what you said, but then maybe make like a little adjustment at the end.
So would you give the distance without like a negative or a positive, just because it's like just?
We're going to have to consider the plus minus at the end. That's kind of the one caveat to this. We'll just have to be smart about that at the end. But I think the setup will get us where we want to go. Okay, so I want to see how far you can run with this. I really do. So I've got a distance function. Is it really that distracting? You should see the two of you are just both like if you were had laser vision like Superman, like you would have burned Andy's computer up. Is that what you're staring at? No?
And out the window.
Okay. You guys were, whatever you were staring at, it would look like it was the same thing, and it was super intense. And I'm like, what exactly? I thought it was Andy, but maybe it was out the window. Sorry. I feel like I've set you up for success, right? Given you a distance function, vertical distance function. Your job is to figure out on the interval from 0 to 12, that's an x interval, what is the maximum vertical distance? Okay? It's really similar to what we did last week, and I know it's been several days, for sure, since last Friday. see if you guys can do this, all right? Remember your candidates. Remember how to test out your candidates. Ready, go. Be considering. Say again? Critical numbers is one category, and endpoints is the other. So I noticed Heather was over there. She was like right on it. And she said, you know what, I'm going to make a table. And she started off and she had, I think she made like a 2-column or 3-column table. I'm going to make a little simpler one. I'm just going to say that I've got X for my input, and then my output is going to be D equals G of X minus F of X. So essentially that distance that I'm trying to maximize. So my input is going to be X, and my output is going to be G of X minus F of X. And can I fill in like 2 of those candidates already that you guys mentioned? I could start off by just saying, well, one of my candidates is when X equals 0, because that's the left endpoint of my domain. And the other one is 12, because that's the right endpoint of my domain. And there might be a few in between. In fact, if I have the graph, I can actually say that there's exactly 1 probably in between, or maybe 2. I don't know. We'll figure it out. And so then, couldn't I figure out those distances right now? I got my distance equation, and I've got inputs of 0 and 12, and I can see from the graph, and I can also see from the math that when X is 0, the distance is 0, right? You just, G of 0 minus F of 0, just 0. Did anybody, you figured out the 12, right? Did you figure out the distance for 12? What was that? Negative 0.719? 711, okay. So there's that. So then all I have to do now is figure out if there's any other candidates. So we've dealt with endpoints already. Critical numbers, though. Ah Young said critical numbers. Critical numbers are places where what is happening? The derivative is 0 or doesn't exist. So if you haven't already gotten into those critical numbers, I want to, again, just give you that encouragement. Start considering where the derivative of distance is 0 or undefined. You can use your calculator to kind of help you along with some of those details. Continue along that process. Kind of done part of it here. See if you guys can continue to wrap it up.
I have a question.
Sure.
Or like, could you?
Sure.
I don't know if this is like mathematically sound. So like to solve for that, like can I take the square root of 4/3 and then cube it?
Let's see here. Let me just, can I trace my way through real quick? I like your derivative. You set equal to 0. You multiply everything through by 12.
Mm-hmm.
Don't lose your equal 0.
Sorry, floating.
Oh, there it is. Yep, no floaties. Okay, that looks good. You flipped it down. You added over. Now, how did this 2/3 become 2/4?
Oh, it did like that. I realized I wrote it wrong, so I like fixed it down.
Oh, okay,
here,
okay,
but,
gotcha.
yeah.
Okay, so then you got 4/3 equals the cube root of x squared. Sure. So then what you did is you probably square rooted this and then cubed this.
Mm-hmm.
Yeah, that's fine.
Oh, okay.
Yeah. You can do it in shorter steps, but that's fine.
Okay.
Yeah. This one up. Hey guys, I want to say something, and I think this is worth hearing for everybody. Like I was jolted into saying this, and it reminded me. Listen, you guys need to hear this. It reminded me that I've said what I'm about to say many, many times over the years. So I want you to hear me out on this. If you are trying to maximize, like in this case, if you're trying to maximize D, you need to set D prime equal to 0/DNE. If you're trying to maximize F, you need to set F prime equal to 0/DNE. So it's got to be specifically targeted at the thing you're trying to maximize or minimize. And if you do that, you should be set up for success. If you do different things, you're going to be maximizing or minimizing other things beside the thing you're supposed to do. So I'm going to set this up as D prime equals, so the derivative of G would be 1/3 x to the negative 2/3, and the derivative of f of x would just be 1/4. So that'd be a key step, right? We find D prime by doing the power rule a couple of times. And then I'm going to go ahead and consider where is D prime not exist? When x equals 0. That's right. What's so bad about x equals 0?
It's a horizontal.
No.
X equals 0. Oh, x equals 0, sorry.
Yeah, you said when x equals 0, we have a DNE. And I agree with you. I'm just wondering why. What's the deal?
Because you have to move the x down into the denominator since it's
It's really a denominator. You're right. And so that would put 0 in the denominator, hence the d any. But you know what? We already have that as a critical, as a candidate, don't we? Right? That's already our left endpoint candidate. So we don't have to add anything to that. But I do need to do this. And this is, as I walked around, you were not the only one that was like, what do I do with that? Right? So I do need to set this equal to 0. And so the algebra here is not trivial. It's not like, oh, just no problem. It's super easy. Some pretty challenging steps in here. So maybe the first thing we do, this is what typically people will do, is they'll add the 1/4 over, right? They're like trying to delay the inevitable, delay like the dealing with the x to the negative 2/3. So they'll just add 1/4 over, and that's fine. So they get 1/3 x to the negative 2/3 equals 1/4, right? And then they're like, well, I know I don't like that 1/3 over there by the x, and so what do? Divide by 1/3, aka multiply by 3. So they get here, and they say, all right, so that's equal to 3/4, and then they're like, what do I do? So there's a number of things you can do here. Can I present a couple of them? Do you want me to start off with the really slow way and work my way to the fast way, or start with the fast way and work my way to the slow way? Fast first?
Fast and furious.
Slow first?
Slow and furious.
What do you guys think?
Slow.
Slow first? We'll go with slow first. You guys were the deciding vote. Okay, so here would be a slow way. And I'll do this, then I'll erase it and show you the fast way. So you could look at this and say, all right, negative exponent, doesn't that mean flip down? Okay, so then it would be 1 over x to the 2/3, and that equals 3/4 still. Then you might look at this and be like, hey, that's a proportion, right? It's a fraction equals a fraction. Can't you just like cross product that? Cross multiply? So that would give you 4 equals 3x to the 2/3. And then you divide by 3. At this point, you're probably thinking, I feel like I'm showing a lot of steps here, and you are, but it works. And then maybe at this point, you would interpret what x to the 2/3 really means. It means the cube root of x, either cube root of x squared or the cube root of x quantity squared. Yeah, it's either way. Basically, the denominator is the root and the 2 is the power. It's, you could go either way. And then, because of this, wouldn't you square root both sides? And then because of this, wouldn't you cube both sides? And is that that's basically what you did. And what did you get, Anna?
I got 1.540.
You guys agree with that? Those of you that maybe got to an endpoint there? Okay. So that equals x. And to me, that would be one of the slowest ways, but it's true. I mean, like if you look at the steps, you're like, are all of those steps logical and defendable and true? Yeah, there's no problem with it at all. I would like to present an alternative. Is that okay? So I'm going to erase these steps. Let's see here. I'll erase. I will get to here. Let's just say I got to this point. And we can actually get to the end here in one step. Whenever you learn back in Algebra 1 and Algebra 2 and Pre-Calc and true in calculus as well, if you're solving for x, doesn't that imply that you're solving for x to the first? Like if it says solve for x, isn't the implied exponent on the x a 1? Right? So when you see this, I'll write it out here. Solve for x, which is essentially what we're doing. Technically, it's x to the first. So here'd be a way to do this in one step. You could say, all right, well, the x kind of is by itself, but it's got that exponent that I don't want. I want the exponent to be a 1 instead of a negative 2/3. So the question is, how do I turn a negative 2/3 into a 1? Not factoring. Because I got to do the same thing to both sides. I can't add something to the exponent. I could multiply by something. How do I take anything, multiply it by something else, and turn it into a 1? Reciprocal. There it is. So if I take this side to the negative 3/2 power, remember if you have a base to a power, you multiply your exponents, and that would give you x to the first, which is what we wanted. And then you can take this whole side to the negative 3/2 power, and then you turn to your calculator for sure. I think that would make this much easier, because I don't know what the square root of 3/4 is off the top of my head. And then cubing it, I don't know that either, but I'm guessing it turns out to be about 1.540 something, right? So you could do that in one step. You can do it in like however many steps that other way was. I don't really care as long as you can get to the thing you need to get to. What do y'all think? So there's only one critical point in between the two endpoints. So I have a total of 3 candidates. I've already dealt with 2 of them. So I just need to figure out what's going on with this final candidate, 1.540. And one word of caution, encouragement here. I bet you it's 1.540 ... right? There's probably a bunch of other decimals there. Do not round early. Do not round early. So when you go to plug the 1.540 whatever into your distance equation that we have up there, make sure you plug the whole thing in. Store it, plug it in. Okay? So has anybody figured out what that distance would be? 0.769. Somebody said, wait, what?
There was 2 different answers. I was sorry,
I thought I heard something else. Yeah, so that's why I clarified. You guys okay with that 0.769? Okay, so then we got to look at this and say, well, what is the maximum distance? And this is where we want to be super duper careful. This is clearly not it, right? Clearly 0 is the minimum distance. Then I got to compare this with this. And this goes all the way back to what Anna brought up at the start. We want to consider just the absolute value of these because we're just talking about a distance. We don't really care whether F is higher than G or G is higher than F. We just want to know what the max distance is. So of those 2 remaining numbers, which one actually has the higher absolute value? 0.769 does, right? Yeah. So I'd say something then like the max distance is 0.769. And all my work is my justification, right? All my work is my reasoning there. I've considered all the candidates. I'm good. So we chose to do G minus F, right? If we had chose to do F minus G, wouldn't this have been a negative number? And this would have been a positive number? But the max distance still would have been 0.769 because distance doesn't really care about plus minus. It just wants to know what's the biggest absolute valued number. Okay. Hanging in? Picking it up? Any questions? Okay, we got a really quick one here, and then I want to point out a couple things, and we'll be doing the mean value theorem, a.k.a. the speed trap. Okay, so last question here, just very conceptual. Decide, we'll just do this together here. Feel free to ask questions as we go through this. Decide whether each labeled point is an absolute max or minimum, and then we're kind of foreshadowing here, but a relatively high point or a relatively low point, okay? Relative max or min. So what do you guys think? A. Is A an absolute max, min, relative max or min, or neither? Point A. It's the absolute min. You are right. So A is the absolute min. Why would you say that? It's literally, that's it. It's the lowest point. Like there are no other points on that interval that are lower than that point. So that's the absolute min. What would you guys say about B? This one's tight. So if I draw a horizontal line here, do you see how there are points over there kind of close to G that are higher than B? I know, but remember that, and this is kind of based on what we just did. If we're finding an absolute max, doesn't that mean that there are no other points on the interval that have a higher y value?
So it doesn't matter if it's closed or
Well, let's not get into that yet. Let's just think about what a max or min is. Doesn't, like if I say this is absolutely the highest, doesn't that mean that there are no other y values that are higher? And we can see some over there on the right side. Now, I agree, there is an open circle over there. We need to deal with that in a little bit when we get to G. But for now, can I say that there's a lot of points higher than B? But isn't B sort of a high point? So I'd call it a relative max. Yep. Relative max. How about C? Yeah, none. None of the above. NOTA. None of the above. Okay, how about D? It's a relative min, right? It's not the lowest, but it is a relatively low point. It's like a little valley. It's not the lowest, but it is a valley. So we'd say relative min. How about letter E? That is, yeah, that's a relatively high point. There are points higher than that. And in fact, B is higher than that, right? But it's a relatively high point. The graph goes up, then it goes down. It means makes it a relative max. How about F? Say again?
Is it any better?
I think F is something. I think it's a relative min. Yeah. Yes, ma'am.
So the reason why C was nothing was because it was like it went through.
Yeah,
Not
well-
because it was on the x-axis.
Yeah, nothing to do with the x-axis. It just, like, I like to think of these as, like a graph like this. I'd like to think of this as like, maybe like a satellite mapping of like somebody driving through the mountains, right? So, point B would be like reaching the top of like Loveland Pass, right? You went up, 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 you hit the top, and you drop down, right? And then D would be like you reach a valley, you maybe reach like Frisco and you start back up Vail Pass, right? And then E would be the top of Vail Pass, so on and so forth. C, wouldn't C just be like halfway down Loveland Pass? You're not relatively high in the mountains, you're not relatively low, you're just like sort of in between somewhere. So wherever a graph of F like this goes from up to down, you have a relative maximum, or down to up, you've got a relative minimum. But stuff in between, it would be none of the above. Be neither. Yeah. Question?
How does relative differentiability play into this?
How does differentiability play into this? So we'll get into this when we get into 3.3. So like the relative min and max thing, I'm foreshadowing a little bit. So I'm not expecting you to have like perfect grasp of that right now at all. But you can have a relatively high or low point at a point of non-differentiability. In fact, we have one right there at E. I mean, E looks pretty sharp to me, and I think F looks sort of sharp as well. I mean, you got to admit, like, if a graph goes from here to there, that's a relatively high point. And it happens to be a very pointy, relatively high point, but it's still a relatively high point. Yeah. Graph has to be continuous, but differentiability doesn't play into that. Okay, let's finally talk about the one that is maybe is going to be a little bit harder to grasp. G. What's G? It's nothing. You're right. None of the above. Anybody have an issue with that? You can argue. Go for it. No, please do. I think there's...
I don't have a good argument. Just
Okay.
doesn't make sense.
Can I argue with... Oh, hold on. It doesn't make sense, but I don't have something I want to argue about. Can I... Oops. Let me fix that. Can I argue for you?
Sure.
Okay. So there's my horizontal line again. Right there, just barely kissing B, right? We're going to go back to the thing you brought up, right? So if you look over this carefully, this graph has an absolute min. It's got a bunch of relative mins and maxes. But do you see how there is no mention of an absolute max anywhere? Like the one place where you might have thought there was an absolute max, we put none of the above, right? So what somebody might say is, and I don't know, Eden, if this is what you're going for, somebody's going to say, well, hey, there's a point right there that's higher than B. Totally true, right? You can see it. I drew my purple line again. But then, so you might say, hey, well, that's the absolute max, right? Because it's higher than B. So the absolute max would be whatever that Y value is. But then couldn't somebody come back and say, well, you know what? I thought of a different one right about there. See how that's a little bit higher? And I think that's higher than your point. Well, couldn't somebody one-up that person and be like, you know what? No, I found one that's even higher than that. Barely, but it's higher. Couldn't we just one-up ourselves for eternity? And we'd never actually arrive at a point where we would all agree that, yeah, that's the highest. Couldn't we just keep adding a number onto the end of the decimal, whatever it was? And so because G is an open circle, we have an open interval on that side, like the question I guess you could also say is, how close could you get to G? Couldn't you just keep getting closer and closer and closer and closer? And the minute you stop and say, and that's the absolute max, couldn't somebody say, nope, I kept going. You didn't count far enough. Somebody could, right? And so for that reason, we would say there is no absolute max here because of the open circle, the open interval over there. If we filled in G, then sure, G absolutely is the absolute max. I get it, but because it's open, we can't declare any point to be the absolute max. Andy?
The should the absolute max be like a limit? The limit?
No, so the absolute, that's a great question. So remember, keep in mind the difference between a limit and the value of the function. So you might say the limit as x approaches g, I guess. I mean, it's hard to tell if g is a y value or an x value or what, but limit as x approaches g, point g of f of x equals whatever. You know, maybe you say, we'll just put a number to it. Let's say equals 10. Let's say that that's what the y value is up there. That doesn't mean you can say f of point g is 10. In fact, you absolutely cannot say that. So in order to say that something is an absolute maximum or an absolute minimum, you have to have actually a point on the graph that represents that thing. And a limit will like help you understand the pattern as you get closer and closer. That might help you understand where you're headed, but you can't say, and that's the max, because the limit never says, and that's the location on the graph. It just says, here's the pattern. Good question. Way to bring limits back into this. It's good. Anybody else? Okay, cool. So in this unit, in this chapter, you're going to see at the end of most of the sections, you're going to see something like this. And you might think, well, gosh, why on earth would you do that? Because if you read that, when finding absolute extrema of f, the candidates are endpoints and critical numbers, which f prime is 0 or d and e. When testing the candidates, evaluate f of x at each candidate. Isn't that essentially what we've been doing? You might think to yourself, why on earth would you just repeat yourself after we just did all this? Here's why. When we get into section 3.3 and 3.4, we're going to be looking at other things like relative mins and relative maxes and inflection points, things like that. And it's going to be really easy for things to start getting jumbled up. Maybe you noticed at the end of this notes packet, maybe you noticed that there was like a lot of like kind of summary material. Like there's a couple of flow charts and things like that going on and some other like kind of summary statements like this. The reason is it's super easy to get these things mixed up. So I'm trying to encourage you to like to have these key takeaways, right? So if you're the type of person that makes like a flashcard for key skills or properties or whatever, like this kind of thing would be on a flashcard, right? You'd put absolute extrema on one side and then something like that on the other side. You could be like, okay, absolute extrema, I need to do this, right? Because later on you're going to be like, relative mins, I need to do that. And relative maxes, I need to do that. And inflection points, I need to do that. The first derivative test, I need to do this. Increasing, decreasing, I need to do that. There's going to be a lot of these that will build on each other. And if you don't take the time to be purposeful about distinguishing what means what, in the end, like no joke, you're going to be writing stuff like this. Well, it's a max because that one thing did the stuff to the other deal. And so there, yeah. That's going to be, and you're going to write that down, you're going to realize, oh, that was terrible, right? But if you've taken the time to be really structured and systematic about the way you think about it, you're going to say, f has a relative minimum because f prime of 3 equals 0 and f prime goes from negative to positive at x equals 3 or whatever. It'll actually make sense, right? So anyways, I just throw that out there. It might not make sense now, but later on it will. Okay, so the mean value theorem, here it is. So this was the speed trap project. We're gonna math this up a little bit. And I'm going to refer back to that speed trap project a lot. We're going to draw some pictures, and I think it's going to go, I hope, it's going to go really, really well. So here we go. Come on. There we go. All right, so here's the mean value theorem. I'm going to read this to you, and I'm going to try to draw the connection back to the speed trap project. So here it goes. If f is continuous on a closed interval, a to b, and differentiable on the open interval, a to b, do you remember, drivers, your excuse that you eventually came up with was, we have a car that can teleport. And that, as unrealistic as that is, if you had one of those, it would have explained a lot, right? And so when you look at these two conditions, f is continuous on the closed interval and differentiable on the open interval, if that's true, then you don't get a teleporting car, right? Because a teleporting car would create a continuous and discontinuous and non-differentiable graph. So as long as f's graph is continuous and differentiable on the interval that we care about, then there is some number on the interval, they're calling it c, there's some number on the interval such that, and here's the hypothesis. On the left, this is the instantaneous rate of change. I'll just put ROC for rate of change. Instantaneous rate of change. And what on earth is that thing on the right? Police, come on, what did you use, police? How did you convict them? What did you do? Use
Average speed.
average. There we go. So an average speed, and speed is the rate of change, right? So the right side is the average rate of change. And for some reason I'm writing out rate of change this time. Could have just written ROC, rate of change. Can I write the right side a little bit differently? Maybe in a way that you're a little more used to? Couldn't I say that the right side is really this? Change in y over the change in x? That's an old school average slope that you learned in Algebra 1, Algebra 2, Geometry, and Pre-Calculus. And in this class too, right? So that right side is simply an average slope, which would give you an average rate of change for our speed trap, the average speed. So what this is saying is that as long as those conditions are met, and we know that your average velocity is 45 miles an hour, we know that your speedometer actually read 45 miles per hour at least one time during your little drive. Does that make sense? Let me draw a graph for you down here. Let's say, this will be a little more generic. Let's say I've got a y-axis and I've got an x-axis, and I've got some graph. Let's go with a graph that looks like this. Oops. Does that work? So there's a graph. This is a graph of f. It's a graph of f. And I'm going to say that this is point A, and that's point B. Is this making sense as far as the setup goes? I've got a graph of f. I've got the interval A to B. Can you see how this is continuous and differentiable? At least I did my best. Okay. So then this, sorry, Jane, this red line right here, what would you guys say that red line could somewhat represent? It's the average slope. Like, the slope of that line would represent the average slope of the blue graph, right? So here's what the mean value theorem says. As long as that blue graph is differentiable and continuous, which it is, doesn't there have to be at least one point on the blue graph that has the exact same slope as the red graph? Can you see it? Where do you think those points would be? Because they have to be there according to this mean value theorem. I think the endpoints are too steep, right? Like if we drew a slope here, it'd be something like that, wouldn't it? Too steep. And over here, similarly, too steep. Well, horizontal, you see how that doesn't match the red graph? I didn't quite draw that.
Thinking of something easy.
So that doesn't match the slope.
No, I know too, because like usually.
How many do you think there are? Anybody have an idea on how many different places? I think there's 2, and I would say there-ish. And no, I missed. Something like that. So this was my original average slope, and you see how those other 2 red lines are parallel to it. Do you see any other spots in the blue graph that have a similar characteristic, similar property?
Is it always going to be twice or tangent
Nope.
once?
It could be 10,000 times,
But the principle just says once.
at least once. Okay, so check this out. Here is my interval. I'll keep roughly the same average. But what if my graph did this instead? There are definitely graphs that do this. So then your average slope would still be that. But instead of just 2 times, how many times do you guys see now? Let's count them up. So I'll use a different color here. So purple. So here's my tangent line. There's 1, 2, 3. Oops. 3. Why is it doing that? Come on.
So couldn't you draw
3,
one tangent line that touches like
4.
technically 2 tangent lines?
Well, I don't know if they're the same one. They seem to be lining up pretty nicely. But the point is, they could even be the same line. The question would be, how many times does the blue graph have that average slope? 5 times. It could even be the same line on the top and the same line on the bottom, like it sort of looks like up there. And you can see that if I just included more and more turning points, there could be like 20 or 30 or 40 times.
The derivative equal to whatever that average slope was, you could find all the points.
And lovely that you would say that. Isn't that what this is? The derivative set equal to that average slope. No, seriously.
Sorry.
Isn't that what you just said?
Yeah.
It was really well said. It was awesome. So informally, if f is continuous and differentiable, somewhere the instantaneous slope equals the average slope. And isn't this the exact principle that our police used? They said, hey, we figured out your average speed, therefore we know that you had to actually go that average speed at least once. And we knew realistically it was probably more than that, but we could for sure guarantee that they went that average speed at least one time. It could have been 2 or 3 or 4 times. We don't know, but it was at least once, wasn't it? That makes sense? So, do you guys remember the IVT, the intermediate value theorem? It's a little different than this, right? But do you remember, like, the challenge with that is the IVT doesn't, like, really give you an answer. It just says that there is an answer. This is the same thing. This is called an existence theorem. And all this really says is, hey, you know what? As long as f is continuous and differentiable, there is an answer to that equation. It doesn't tell you what the answer is. We'd have to take some more steps to actually figure out what that answer is. But it tells us that the answer either does or does not exist. Make sense? Let's do a couple of examples here. We'll probably do 2. See how it all goes. So please take a look here. Let me just look. That one, I don't know. We'll see how it goes. Let's do number 1. I would say this is scaffolded, kind of like what we did before. I would say this probably goes relatively easy, relatively medium, relatively difficult. We'll go in that order, okay? So take a look at example number 1. So it says, determine whether the mean, and by the way, MVT is an acceptable abbreviation for mean value theorem. Just put MVT. So determine whether the MVT can be applied to f on the closed interval a to b. If the MVT can be applied, find all the values of c in the open interval AB so that that equation is true. If the MVT cannot be applied, explain why not. So we're getting at the conditions here. So let's address this first. Determine whether the MVT can be applied. What are the 2 conditions for the mean value theorem? Continuous and differentiable. So the function has to be continuous and differentiable on the interval that we're considering. So let's take a look at our function now. Let's actually see what it is. It's f of x equals x to the 3rd plus 2x. Do we know? Is that function differentiable and continuous, or are there going to be some issues with that?
It's both.
It's both. Why is it both? It's a cubic, and more generally, what kind of a...
There's no numbers to make that.
Yeah, totally. What kind of a function is that? It's got a special name that scares Algebra 1 students. Polynomial. There you go. Polynomial. It scares Algebra 1 students. We do polynomials. They're like, Poly what? I get it. I totally get it. Okay, so we'd say something like, because f is a polynomial, it is continuous and differentiable on our interval. Therefore, the MVT applies. So basically what we've, by recognizing that, we have guaranteed that this equation right here has a solution. At least one, right? There's at least one place where the instantaneous slope or the instantaneous rate of change is equal to the average rate of change.
So would you always want us to define it as a polynomial, or could we just say that, like, it's continuous? Or, like, do we need to state, like, the reason?
I think typically you can just say, hey, it's continuous and differentiable because I just know it.
Yeah.
Unless you're asked to like prove that, you can usually just recognize it. So if that's true, then somewhere the instantaneous rate of change equals the average rate of change. Okay, so this asks us to take that additional step of, hey, you know what? We know that there's an answer, and now let's find it. Does that make sense? We're actually going to find this. So this is a cubic, kind of like my original blue graph earlier. So if I'm going to work with this equation, I probably should know what f prime is first, right?
Yeah.
So what's f prime? 3x squared plus 2. And that has to equal f of b minus f of a over b minus a. What are my b's and my a's here?
91.
Isn't it the endpoints of the interval? Yeah, Nick, you're right. So this would be f of 1 minus f of negative 1 over 1 minus negative 1. What do you guys think f of 1 is? 3. What's f of negative 1? Stu, how you doing, buddy?
Good. I'm trying to do it in my.
Okay. So what do you guys think f of negative 1 is? Negative 3, yeah, so it's 3 minus negative 3. Of course, that's over 2. So it's 3x squared plus 2 equals 6 over 2, which is 3. And now we just need to get busy solving this. So you subtract 2 from both sides, divide by 3. And how do we finish this one off? There you go. Yeah, but you got to do the plus or minus here. So plus or minus 1 over square root of 3. And you are allowed to leave radicals in the denominator, like I mentioned earlier this year. So you just stop right there. Now you always want to do one last double check and make sure, are both of those numbers actually within our interval? Yeah, because 1 over root 3 is definitely less than 1. So those would be your two places. This is a cubic, so you could easily graph this on a window and see the two places on the graph where the average rate of change and the instantaneous rate of change are the same. So to parallel this back to the speed trap project, what we just did with all of this, is we said, not only do we know you sped, we know exactly when you sped. Right? That makes sense? When x was equal to plus or minus 1 over root 3. Like, that's where the analogy falls apart a little bit. But we're taking it to that next level of saying, hey, we actually have a graph, a function for your, the way you moved, and we know exactly when you were speeding. We couldn't do that on Friday. We could do that today. Any questions?
Do they actually do this? Or do they not care?
Does who do what?
Does anybody ever, do police ever actually, figure it out?
So we talked about this a little bit on Friday. So absolutely, it's acceptable in a court of law to say we know your average speed. Therefore, we know so think about this. Our police never, did anybody get caught speeding on the radar gun? Nobody, right?
Or on the
Andy.
Oh, Andy did a little bit. So other than Andy being a little quick on the trigger of the the whole accelerator thing, no one was actually observed speeding with the radar gun. Nobody got the radar gun pointed at them and the reading came back speeding. And even though we did with Andy, we still got in for more because we said, we never saw you speeding. We never saw you going 45, but we know that your average was 45. Therefore, you had to go 45 at least once. Totally acceptable in court as long as you have the documentation. I mentioned on Friday that they'll sometimes use airplanes, helicopters. They've used those in the past to actually...
Yeah, they do that in Florida on those big highways.
Right, wide open stretches and... Yeah, because it's just too easy, right? So anyways, yeah, they'll mark the pavement sometimes and they'll literally just hit a stopwatch and say, all right, they just passed mark number 1, and they passed mark number 2, and they hit another stopwatch. They'll radio down to the car and they'll say, hey, the blue Lexus was just averaged 92 miles an hour on that stretch, so you probably ought to pull them over. Yeah, Jane.
I heard in some states when you use a toll road that they're checking for that and they can charge you
Yes.
addition to your toll.
Yes.
Your ticket.
Now, C470
You
Prime...
can't get points for those
You can't just take a
stationary
nap.
things. So you
C470 prime example of that, right? Because it's automated. It's super easy. And Jane, you're totally right. Because they know the distance and that there's no shortcut between the toll. If you take any other route, you went longer, right? And they know the exact distance between the toll, things, the toll little cameras, I guess. And so if they want to calculate the time, they can get your average speed and whoa, somehow you averaged 97 between those two toll things. And you might deserve a really strong ticket. So yeah, totally.
They have vans now in Colorado, just sitting cars inside.
I know.
Have you gotten one?
No, I see them and they make me mad. I'm like, hey, because there's nobody in there, just a camera, It's yeah, I know. There should at least be a person
You
in there.
can't get points for it, you just a fine.
Well, yeah, $100 is $100, whatever. Yeah, Andy.
That's a lot better than insurance.
That's true, yeah, over the course of 5 years. Good point.
So probably like when they do that, like they calculate the average speed.
Yeah.
Like they do that in China, but like people would just like speed and then they take a nap in like a service station.
I haven't been yet.
It kind of
It defeats the purpose of speeding, other than just to go fast,
yeah
right? I mean, if you just want to go fast, I get it. But if you're not, if you're trying to get somewhere,
yeah
it totally defeats the purpose.
Or you hit the next mark.
yeah.
Right? Yeah. So like you go like 120, but then just like stop and wait there for a few minutes or whatever,
Yeah.
and let your average drop back down to the appropriate level, like the time that it would need to
I guess
not get a ticket.
it does kind of make sense. I guess you can get some like rest. I guess.
Yeah, I suppose.
Yeah.
Depending on how long the stretch of road is, right, and how fast you're driving, right.
Yeah.
So the sad thing is, the faster you drive, the longer the nap, right?
Yeah.
I don't know. That might not be a good plan. Who knows? I really need a nap, so I need to go like 140 or however fast my car will
Well,
go.
if you're like going like a long road trip, like,
I know, I get it.
Yeah. you
But
can
what if
drive-
a horse like runs out in front of you, or a deer, or an elk, or a rabbit, and you freak out? It broke out of its pen. I don't know. Like you better not hit the horse, right? It's gonna be bad.
Hit deer head on instead of trying to swerve off. You just
Still
take
kill
your
you.
foot off the gas.
Okay, let's take a look at example number 2.
Because they're just gonna
Example number 2. Here we go. So we've transitioned from a speed trap to a generic one to a coffee question. All right. Says hot water is dripping through a coffee maker, filling a cup with coffee. If you make coffee at your house, you know exactly what's going on here, right? The amount of coffee in the cup at time t on the interval from 0 to 6 is given by a. That's a pretty important word, isn't it? So seeing if you were tracking with me, right? Given by a differentiable function c. Guys, can I give you a universal hint? Hey, listen. Universal hint. If you see somewhere where they say, hey, there's this differentiable function, here's what you really ought to do. You need to come down here and say c is differentiable and continuous. Like, I really think you should just be on autopilot at that point and say, hey, you told me that C was differentiable. That may or may not be important. Just in case it is important, I'm going to write down that C is differentiable and continuous because differentiability implies continuity. Yes, ma'am?
Will you ever have to like write that to get a point?
Yes, absolutely. So understanding the conditions for like the IVT, which is just continuity, and understanding the conditions for the MVT, which we're about to do here, super important.
Okay.
And so, yeah, please do.
Okay.
Please do, yeah. Okay, so differentiable and continuous function C, T is measured in minutes. And of course, we get this table. We've done a few tables already where we just have these selected values of C. And this makes a lot of sense because, you know, if you sit there and just stare at the coffee maker, you know, it's like it's a waste of time and it seems like it takes forever. But if you come back every minute or so like this, you're like, oh, not full. You go back and you put your shoes on. You're getting ready for work or whatever. You come back in like 2 minutes or 3 minutes. You're like, oh, not full yet. You go feed the dog and you come back finally 5 or 6 minutes and it's full, right? So you're not going to be checking it every second. So it actually sort of makes sense that you would check it every minute and see this. Yes, ma'am?
So if like you were gonna write it as like the average equation, like 4 minus 2. or,
You're
like,
getting
12.
way ahead. You're getting way ahead of me now, right?
It's just a general question, not like the questions about the actual thing. But like, how do you label that? Like, what do you set equal to like the average slope? Because it's not
Okay.
like,
I think I would probably work my way around that. I would. You could just, if you wanted to, you could just write the words average slope equals.
okay.
Like that would be totally acceptable. But what I think I'm going to do here is I'm going to set up my equation right off the bat. But let's talk about why we would do what we're about to do. The question then says, is there a time on the closed interval from 2 to 4 at which C prime equals 2? So guys, I want you to think about what they're asking. They're asking, is there a time where there's an instantaneous rate of change of 2? They're not asking what it is or when it happens. They just want to know, does it exist? That makes sense? Do you see how they're not asking you for like an actual solution or numerical answer? They just want to know, does this thing exist, this thing we're asking about? Does that make sense? So that should direct you to, oh, this is one of those existence theorems or existence ideas, like the IVT or in this case, the MVT. How do I know it's the MVT? This is really important, guys. Look at your table. Your table gives you information about C, but they want to know, is there a place where C prime, which is the slope of C, right, equals 2. That tells me I need to be considering the slopes of C as opposed to the y values of C. So here's what I'm going to do. The interval I care about is from 2 to 4, and this is kind of what Anna was getting at. I'm going to go ahead and find C of 4 minus C of 2. There's too many C's in there. No, there's not. C of 2. A lot of parentheses and C's gets a little confusing. There we go. Looked bad, but now it's better. So it's kind of floating right there right now, isn't it? I'm going to say C prime of 4 minus C prime of 2 over 4 minus 2. I'm going to say equals C prime of T. I don't know what it equals yet. That's my equation. I'm going to say I want to know, is there any place where the average slope and the instantaneous slope are the same? So all I got to do here is figure out what C of 4 minus C of 2 over 4 minus 2 is.
So say this like came out to equal like 3.
Oh, yeah.
Or like with the speeding thing, like if like it clocked him at like 46, does that imply that like the change of speed was like
Then we'd have to get it.
45 at one point?
That would be that. Well, so then we'd have to get into an IVT thing, which we can talk about here in a second. So check this out. So C prime of T equals that. And then when you actually figure out what that left side equals, 12.8 minus 8.8 is 4. 4 over 4 minus 2 is really 4 over 2. And look, it's 2. So I figured out that the average slope was 2. And because C is differentiable and continuous, this is the speed trap project in a nutshell, isn't it? I figured out the average rate of change. And because I have a differentiable and continuous function, doesn't that mean that I have to have that average rate of change show up instantaneously at some time on the interval? The speed trap project. You averaged 45. We know that you went 45 because you don't have a teleporting car, right? And so you could say, therefore, yes, there is a time. But you've got to have the conditions, I should say, and then you've got to have your showing of how you figured out that average slope. So Anna asked an interesting question. She said, what if you did all this stuff over here? What if you did all this, and instead of getting 2, you got 3? You didn't make any mistakes or anything. Let's just say you got 3. Would that be enough?
Yeah.
The answer is no.
No.
You would need to use an IVT type logic. So if I showed,
So you'd have to show a time when the slope was below.
there you go. If I could find another interval where C prime averaged to be, say, 1, I could say, well, hey, over here C prime is 1, and over here C prime was 3.
And by another interval, you mean an interval within that, so like 2 and 3 between. Like
Yeah,
2 and
between
3?
like 1 and 2 or something like that.
Wait, 1 and 2 wouldn't be in the interval.
Well, the question would have to be a little bit different.
Okay.
I would have to say,
Like if the slope between 2 and 3 was 1.
yeah, we'd have to consider some other ones, some other slopes, some other interval slopes. Yeah, so we'd have to rework the question's wording a little bit, but you'd have to use that kind of reasoning. Yeah. Questions? Are you seeing maybe the usefulness, purpose, the intent at least of the speed trap project? Is it making sense? Okay. Okay, let's take a look at the final one in here. Example number 3. And what shows up is a piecewise. Yeah. Embrace the piecewise.
I just hate writing out to figure out if it's continuous. Like,
Yeah, if this one's not continuous.
Don't. There's something beautiful about that. The precision of the writing. Yes, there is.
Yeah, but then it's like a lot of effort.
Oh, so
much effort.
it's all about effort now.
Yeah, I'll give it.
I am sure glad that Michelangelo was like, I could create some really beautiful things, but you know what? It's going to take some effort. And darn it. Aren't you glad that the person that came up with the cell phone and the personal computer wasn't like, this could be beautiful, but effort.
No, but
They're
it's
like,
different,
oh, I'm
like,
gonna
it's
make a
not
lot
like
of
you
money
could skip
off
the
of
step. Like, I bet if you could have someone go
You know what they were really good at?
all the products for him. he
Math.
would've-
So this could be you.
This is like.
Could be you. Or not. We don't know. We don't know yet, but it could be you. Okay. That's the point.
No, but you can still do it without writing out. You can still find
So-
out continuous without writing out.
So guys, Yang, your question real quick. I want to make sure we wrap this up. Go fast.
Why is there not a less than?
Oh, shoot. That's a typo. Hey, guys. Hey, listen up. I don't want to, guys, I do not want to cram this all into the final minute of class. So let's start now. There's a typo here, and it's just a straight up typo. Sorry. Let's make, because otherwise this makes absolutely no sense. Let's please change this greater than down here. Let's change it to a less than. So the pi is, yeah, thank you for noticing that. Okay, so guys, again, we can do this here pretty quick, but if we wait until 23 after to start, it's going to be unpleasant. We can do it pretty easily right now. So notice the wording on number 3 is really similar to the wording on number 1. It says, determine if the MVT applies to this. And if it does, we're going to go ahead and complete the hypothesis of the MVT and find the value. But if it doesn't, the MVT doesn't work here, then we're going to explain why. So Bailey brought this up. We always want to test, and this kind of goes to Maddie's question, we always want to test to make sure that the conditions for the MVT are met, because if they aren't, don't we just say it doesn't apply? And you're done. You see how that could potentially make this a very quick, or relatively quick question. So we need to check the conditions. What are the 2 conditions for the MVT? Continuity, differentiability. You need to have those down solid. We'll keep practicing with those, but continuity, differentiability. So here we go. Continuity. Remember, if you're going to make any claims about continuity, what do you have to use? One-sided limits. There we go. So I'm going to write the limit as x approaches pi from the left, and that would be the x over pi plus 3, now that we've corrected the piecewise, is possibly equal to the limit as we approach pi from the right of the other piece, 4 sine of x over 2. And that's supposed to equal g of pi. So let's evaluate this. So the first one, as I apply that limit as x approaches pi from the left, what do I get?
4.
Yeah, pi over pi is 1 plus 3 is 4. Equals sine of pi over 2, right? What's sine of pi over 2? 1, and then times 4. Yes, 4. Look at that. And of course, g of pi is contained within the sine piece. So 4 equals 4 equals 4. Continuous, right? It's making sense? This is where you say yes or no.
Yes.
Okay. Hoping you're seeing the similarity between stuff we've done before. Now we got to check differentiability. I'll just put diff for that. In order to do this, we need to find what f prime is. So it's piecewise, so I'm going to write f prime equals, what's the derivative of 4 sine of x over 2?
4 cosine.
So 4 cosine of x over 2, I agree, times 1/2. It's a chain rule, right? So I'm going to write 2 cosine of x over 2 for x bigger than pi. Chain rule factor is 1/2. 4 times 1/2 is 2. And then the other piece is much easier, perhaps. What's the derivative of x over pi plus 3? 1 over pi. Good. Very good. Okay. So now we're going to find that this finishes immediately, because when we continue to consider differentiability, the limit as x approaches pi from the left of 1 over pi equaling the limit as x approaches pi from the right of the other piece, 2 cosine of x over 2. They're different, aren't they? From the left, you get 1 over pi, and from the right, we get, what's cosine of pi over 2? Times 2 is just 0. So 1 over pi does not equal 0. So even though this graph was continuous, it is not differentiable. So we'd say something like this to conclude. Because f is, no, is it f? Yeah. No, it's g. Sorry. Because g is not differentiable at x equals pi, the MVT does not apply. So it's always worth it to investigate the continuity and differentiability of those 2 conditions, because if either one is not met, then the MVT doesn't even apply.
Do you have to say at like x equals pi? Could you say it's not differentiable at all points?
So I think it's good to mention either the point or the interval. So if you said not differentiable on the interval 0 to 4, because of course pi fits within that, then I think that'd be okay too. I think it's always good to say here's where, if you can. Sometimes you're not going to be given enough information to say it, and it happened here. In this case, we are. So I think it's always good to be specific. Good as question. Any other questions or thoughts? Okay. So just a reminder to you all, when you guys come back next week, Monday, we'll be actually continuing to use this as we head into section 3.3, and we'll actually spend, believe it or not, we'll actually spend the entire week next week on 3.3. There is an intro video for it for Monday, so make sure you catch that. But we'll spend the whole week on 3.3, so it's a big section for sure. Hope you guys have a wonderful weekend. Stay safe.
On the side, it said that there was like a review that was due tonight.